But as I said, as there is no ohmic power limit, there is typically no need for additional heating, which makes this configuration much simpler from the technical point of view to be realized. So if we parameterize the stability properties of configuration in terms of the safety factor profile, where, of course, there is expression of the ratio in between the toroidal magnetic field and the toroidal magnetic field. Sorry, I take this here. We have on the upper part of the graph, we have the tokamak with the safety factor, which is much larger than 1, which makes typically this configuration very stable and with good performances. On the bottom part here, there is the reversing pinch, which is characterized by a toroidal magnetic field. You can see here on the graph on the left-hand side, which changes sign at the edge, so that also the safety factor changes sign at the edge, where we have the so-called reversal. And this corresponds to a minimum energy state. And this kind of configuration cannot be sustained from outside totally, but it should rely on internal MHD dynamics to be sustained somehow statically. So RFX mode and now RFX mode 2, which is going to start in 2025, will explore this configuration, but RFX mode 2 has a kind of unique capabilities in the European panorama, I would say, for the investigation and comparison of the wide variety of magnetic configuration in the same device. This is due to the fact that RFX mode is equipped with a very advanced multimodal feedback control system, which is made of 192 independently fed active saddle coils, and a wide diagnostic systems made of around 2,000 sensors, which allow the exploration of 3D features in, as I said, a wide range of magnetic configuration. So you have a picture here of RFX mode 2, which has a major radius of 2 meters and close to half a meter of minor radius. So we can explore the reversing pinch configuration with a plasma current up to 2 megaamps. We can explore the tokamak with a plasma current up to around 0.2 megaamps. This is due to the fact that we have a limited toroidal magnetic field. And we can also explore, due to this advanced feedback control system, also all the configurations which are in between the two, the so-called ultra low Q. So as a tokamak, it has been operated in order to explore a wide range of safety factor profiles, including the less than 2 operation, which is typically not accessible to traditional tokamak devices. We achieved the H mode thanks to a modification of the electric field at the edge. And in this device, we can study with some detail the effect of 3D magnetic perturbations, both on L control when an H mode is achieved, but we can also control instabilities, and we can study how this 3D perturbation can avoid, say, disruptions, in particular the formation of runaway electron beams. But RFX mode 2 is also flexible in terms of the shaping that you can give to the plasma. You can produce positive and negative triangularity conditions, and also single and double null, and also the snowflake. So the idea of this device is that, in principle, you can compare in the same say boundary, with the same boundary, you can compare a large variety of configurations. But RFX mode has the main focus on the reverse field pinch configuration, and this is done thanks, as I said, to the exploitation of these MHD sophisticated, I would say, MHD techniques, and we could achieve the 2 megaamp plasma current level, which was the design target, which corresponds to a pure ohmic heating power of around 60 megawatts, which are coupled to the plasma. Why is it important to go to high plasma current? Because we observe a positive scaling of the confinement performances with the plasma current itself. You can see here on the right-hand side how the electron temperature scales with the plasma current. You see that there is a positive, almost linear trend. And also we have observed an interesting anomalous ion eating phenomenon, so that most of the power that you couple to the plasma goes directly into the ion thermal content, which means that we observe a largely enhanced deuterium neutron rate, which is an interesting effect, of course, if you want to study fusion. But the most interesting aspect is that we observe, when we go to high plasma current, a spontaneous transition from a magnetic chaos dominated plasma. This chaos is produced by many magnetic perturbations with almost similar amplitude. And we observe that when you go to high plasma current, one of these perturbations becomes largely dominant, so that it's not more a perturbation, but it becomes a new equilibrium. And this corresponds to a self-organized plasma with largely improved confinement properties. And you see here in red how the electron temperature largely increases in the core when you move to this helical state. But even if the performance has improved, and of course we have performances which are not comparable at present with those of the tokamak, but we really believe that we have a good space to improve them, because we observe that some residual chaos due to small scale stability is still present and still playing a role. So we decided to move from RFX mode to RFX mode 2. So we decided to change the magnetic boundary. We made some major modifications by putting a stabilizing passive copper shell much closer to the plasma, and this should give the possibility to have access to new scenarios with improved capability. You see these big dots in green are the expected scenarios for RFX mode 2 with respect to the blue ones, which are those that we already explored. In particular, because you see that we're going in a region here where residual mode amplitude, which is associated to these magnetic perturbations, will be, or are theoretically expected to be at a much lower level, and this should improve the energy confinement time. These studies are relevant for us because we're trying to understand to what extent it is possible to propose a reversible pinch, which, as I said, is technically simple, as a low-cost volume neutron source, so that you can use it, for example, in a fusion-fission hybrid reactor. Because the production of neutrons is an interesting one, and it is so technical simple that you can think about a reactor where we have a fission part, but with a fusion core. So RFX mode 2 will help in order to understand if we can indeed propose this kind of solution for the next future. So that's all I wanted to say. Thank you for your attention. If you have questions, or otherwise I could give space to floor to Giunluigi Serianni. Can you hear us?
I think, Giunluigi, you should be co-host as well. So I think if you stop sharing your screen,
I'm sorry, I thought I did it.
Matteo, then Giunluigi can.
Okay.
Okay, so again, hello everybody. I will describe the other activity. One of the two main activities will be described today. The other activity that we carry out here at Consorzio RFX, which regards the preparation, the optimization, of the ITER neutral beam injector. So, probably all of you know that in order to attain fusion conditions, ITER requires some additional heating systems. Among them, there will be two neutral beam injectors for a total ejected power of 33 megawatt, and there is a provision for a third one. The injector itself is made of several components, so you have to create the beam particles and accelerate them. They are charged particles, so they should be neutralized, otherwise they do not enter the magnetic field confined the plasma, and then they enter the plasma. The requirements of the interneutral beam injector are shown in the table. The point is that the beam energy, in order for the particles to attain the center of the ether plasma, which is of course pretty dense, is 1 MeV. And neutralizing positive ions, positive hydrogen or deuterium ions at this high energy is very difficult, as you can see on the right-hand side, so that we have to resort to negative hydrogen or deuterium ions, which are very easy to neutralize, but on the other hand, it's very difficult to create a huge amount of negative hydrogen ions in the source. The source is essentially, here you can see the various components. On the right-hand side, the sketch of the source, the CAD view of the source, which is essentially a plasma source, plasma sustained by 8 radio frequency drivers, in which some negative ion particles are generated, particularly thanks to the conversion of positive ions and the neutral atoms, hydrogen atoms, on the grid that you can see, which is made of several small apertures where the accelerator starts. Then you can see the other beamline components, including the so-called residual ion dump, which is dedicated to accepting the particles which were not neutralized inside the neutralizer. So actually, the operation of this machine can be described in terms of discharges. Several types of discharges, of course. The one which is at the center of the figure, the red one, is the plasma. The plasma is the discharge that we really want. But on the other hand, there is a possibility that we have discharges outside the plasma box, where the drivers, around the drivers, the RF drivers, and of course this discharge is not desired. We have discharges inside the accelerators. This is normal operation, although of course they are not desired, but there are some other types of discharges which can be very dangerous for the machine itself. One is between the entire source, which will sit at 1 megavolt, the particle acceleration energy with respect to the vacuum vessel and the vessel itself, and particularly along the 1 megavolt power supply line. This one is a showstopper, so we cannot accept any discharge in this component. I'm stressing this because actually this happened. So we had a major stop in the preparation of the one-to-one of the entire copy of the accelerator just because of this. Okay. So one of the specific features of the ether neutral beam injector is that the whole source is in vacuum, is in the same vacuum as the ether plasma, which means that it is difficult to have a complete insulation of the source. That is why I'm stressing, I stressed earlier this voltage holding feature, which is required. And it is also a very large plasma source, so that three-dimensional effect cannot be neglected. So we have, for instance, a non-uniformity across the beam, which is due to the fact that we have plasma drifts. Just to name one of these aspects. And also there is a possibility that the RF drivers, that there is a crosstalk between the RF drivers, they interfere, which makes things even worse. Okay, talking about the physics that occurs, we generate a plasma inside. I use numerical simulations in order to clarify what's going on. We have a magnetic field, which is in this picture is vertical, although in reality it's horizontal, this is the RF driver in which the plasma is created. Of course, here the temperature of the electron is high, but and it is very useful in order to create positive ions and to dissociate the hydrogen. These two particles are the precursors of the negative ions to be created at the end of the plasma where the accelerator starts. On the other hand, here we do not want electrons to be hot, because otherwise they will very effectively destroy the negative ions, as you can see on the left-hand side of this reaction rate plot. So we need to have a sort of separation between the generation of the plasma and the use of the plasma in order to create negative ions. And this is accomplished by means of the filter field that I described earlier. Okay, so this is what happens, and these are some figures, and you can see also the spatial scale of the source of the interneutral beam injector. Actually, this is a one-to-one copy of the ether source, but not of the entire injector. It is another experiment which is called SPIDER, which has already operated for 3.5 years. Now it is at the end of a 2-year-long shutdown. We are really closing the source today. Yesterday the accelerator and the source were separated. Today they are joined together, and in a couple of months we will resume the operations. The operations. Here you can see some results of the last campaign, the previous campaign up to 2 years ago. You can see the amount of negative ion current, and unfortunately, another figure of melting, which is very important, is the amount of electrons which are extracted together with the ions. Of course, we have to minimize the number of these electrons. So the real operational point is on the left-hand side and at the top of this graph. Just to compare with another source which is not dedicated to ether, but it is very important because it is essentially half the size of the ether source, which is operating in Munich, the ELISE source. Here are the data obtained in ELISE, and in the same range of parameters, the RF power which generates the plasma. As you can see, we are in the same range. We have to improve, to increase the RF power, and this will be the aim of the next campaign. This is one of the activities we have performed and we are performing. With respect to other sources which are operating in Japan, which are not based on the RF generation of the plasma, but on filament arc generation of the plasma, we have some features. We have a higher non-uniformity of the plasma, which results in a non-uniformity of the beam. We have larger divergence of the beam, with the tendency of the beam particles, which have essentially the same charge before neutralization, to get wider and wider. So the idea is, and in terms of the plasma parameters, it is clear that we have a lower plasma density, for instance, and a larger electron temperature. So the idea that we have implemented, that we will be studying, is to better confine the plasma. We have added some magnetic permanent magnets. The test will be performed in SPIDER, but the optimization will be carried out in a dedicated facility, which is much easier in which we can operate much more easily in terms of changing the configurations, which is called Minion, which is starting the operation in these days. And going back to the issue of the voltage holding, here you can see some tests of the DC generators up to 1.2 megavolt. This test was successfully passed. This year we will start, and next year in 2024 we will continue the test with the source, with the mock-up of the source, and then in 1.5 years the entire one-to-one copy of the injector will start operation. So this is sort of summary. We have produced interesting results in terms of the plasma parameters and the low acceleration voltage up to 100 kilovolt with the machine SPIDER. We have identified some issues which have to be optimized, and then we will resume the operation shortly. As I said, and Mythica, which is the copy of the entire injector, is being completed. The high voltage tests are going on, and in 2025 we'll start. At the end of 2025 we'll start the operation. Thank you very much for your attention.
Yes, thank you, Gianluigi. I see there is one question in the chat from Ben. I think it's originally targeted at Matteo. Can you please give us more details on the fusion-fission hybrid reactor concept?
Yes, maybe I can say a few words. So the idea is to have a system where a source of neutron can be used in order to induce, for example, nuclear waste transportation, or if you want to produce energy directly to fertilize nuclear fuel. So in principle, if you have a core producing fast neutrons, as those from fusion, these neutrons can be used to fertilize, for example, uranium-238, in order to have a system which is more efficient, but below the critical threshold, so in a subcritical condition. So the idea is that you could use the neutrons, which are fast neutrons, produced by fusion, in order to induce transmutation or fertilization in a controlled way. That's the idea.
That Carlos is
Okay, I think that's quite a good explanation. Oh yeah, Ben is also grateful for it. I think there are no more questions because otherwise, no raised hands. So I think then I would like to thank you, Giunluigi and Matteo, for your presentation. And we can move on with Radomir Pánek from IPP in Prague.
Okay, thank you very much. Bye-bye.
Okay, bye-bye.
Max Planck Institute for Plasma Physics, the branch that is located in Greifswald, Germany.
Good afternoon.
He is working on
Yes, good afternoon.
generator 1.57x.
I can see
he will
some
tell
other
us more about the different activities that are
presentation.
have been taking place.
Yes, you should be able to share a screen.
But I'm hearing probably different presentations. I hear somebody speaking.
Oh yeah, that is Dario in the background. I'm
Okay.
sorry. We are in the same room
Okay, good.
physically.
Everyone, yeah, 1 second. I'm gonna...
So, can you see my slides?
Not yet.
Not yet.
Yeah, you should be able now to share this screen.
Now?
Yes.
Yes, now I can see your screen.
Perfect.
Yes.
Can you see my mouse moving?
Yes, we can see your mouse moving.
Okay, thank you very much. So good almost afternoon. So my name is Radomir Pánek. I'm from the Institute of Plasma Physics of the Czech Academy of Sciences, and I'm supposed to tell you something on what we are doing on the main project which we have now in our institute. And this is the installation and construction of a new tokamak, which is called Compass Upgrade. Yes. Okay. So this is the outline of my talk. So I will first briefly introduce you the institute and our, let's say, former tokamak, which was in operation in our institute, let's say up to recently, and then I will switch to the new project, and I will try to describe you the main tokamak systems. I will try to show you on these main systems which expertise, which skills are necessary to design such a machine. I will tell you something on diagnostics, on control and data acquisition system, and I will finish with some more details on the present status of the project. So, the Institute of Plasma Physics is part of the Czech Academy of Sciences, which is a large institution of 50 institutes. We are one of them. We were founded a long time ago, and we are, let's say, a medium-sized institution, approximately 300 employees. So the research is organized into four research or science division, as you can see on this organigram. So the first one is division of fusion plasma, and later I will speak mostly about the activities of this division. Then we have a division for laser plasma, where we operate large laser infrastructure. Then we have a division which focuses on plasma chemistry and materials. It means application of low plasma, low temperature plasma, let's say in medical applications, in biomedicine. Then also we focus on let's say use of plasma torches, special plasma torches to decompose dangerous waste, to generate hydrogen, etc. And we also develop here special materials using plasma spraying or cold spray technique, also for fusion applications. And the last division is called Top Tech, and this has no connection to plasma. And this is a group large group of experts which developed very special kind of optical systems, and we developed the systems mostly for European Space Agency. So now a few words on our history. So the fusion research in our institute started more than 60-70 years ago. First experimental device was called Castor tokamak, and in 2006 we started a project of a new tokamak which was called Compass. This machine was put in operation in 2009, and we stopped the operation of this machine in 2021. And this machine, the exploitation of this machine was very successful, and it helped us to significantly increase the team, who attract a lot of students, and the team is now, let's say, four times larger than 15 years ago, and is quite young and ambitious. And because the team is ambitious, we started to think how to continue after let's say the era of Compass tokamak, and we came with a proposal for a new machine which will be unique, let's say, in world scale. And we proposed a machine which will be medium-sized tokamak, so not big one, but medium size. But it will be unique in a sense that it will operate at a high magnetic field and with high plasma current. So it will be able to generate plasma condition which will be very close to future European demo fusion reactor. As you might know, there are many tokamaks in the world now which can operate for a long time and under different parameters. That there is, after the shutdown of Alcatel C motor MIT, there is no machine which can reach 4 or 5 Tesla of plasma of magnetic field. It means the field at which TRM and probably also demo will operate. And Alcatel C motor a long time ago showed that at this magnetic field, the plasma behaves a bit differently, or we should expect different behavior of plasma. And there is no such a machine in the world which could, let's say, continue in this research and demonstrate it. So that's why we developed a project of this new machine. So it will be probably it is included in the European fusion roadmap. It will be exploited hopefully as Eurofusion so-called consortium machine or device. And it's being built also in strong collaboration with US Department of Energy, which provides in-kind contribution for this project. The idea of this machine came in 2015, and so we spent 2 years for pre-conceptual design. Then the funding, we were successful to get funding. The funding is on the level of 100 million euro. And we continued with conceptual design and preliminary and then final design. And you can see that when all these reviews were performed. Now we are in the phase of, let's say, tendering, manufacturing, and installation, which is in progress. As you will see later, the project is extremely challenging from engineering point of view, physics and engineering point of view, but it's progressing more or less quite well. On the right-hand side, you can see the cross-section of this device. So you can see the vacuum vessel, which is relatively small in comparison to the size of the tokamak. Outside of the vacuum vessel, you have toroidal field coils and toroidal field coils, and the big gray part here is a support structure. This is because there are extreme forces acting on coils and vacuum vessel, which have to be compensated by the support structure. And outside, we have the cryostat. The whole machine will have to be in cryostat, as I will explain later. So what are the basic parameters of this machine? So if they are shown in this table, so toroidal magnetic field can go up to 5 Tesla. So it means in the center of plasma. If you would go to high field side, we can reach up to 10 Tesla in principle. Then the plasma current can reach 2 megaamps. Main radius something less than 1 meter. Minor radius about 0.3 meter. We will be able to achieve very high triangularities, which is also one of the key, let's say, goal or idea of the scientific program. So to study these effects, so we can go up to 0.6 or even up 0.7 the triangularity and relatively standard elongation. What's important is it will be metallic first wall device. It will consist of tungsten, and in fact it will be the first machine in the world which will be put in operation for the first time with tungsten first wall. So it will be very good test bed for ITER, which probably will change now for tungsten. And it is generally accepted that let's say the starting machine in tungsten environment is not easy at all. And what's another unique feature of this machine is that we will be able to heat the plasma facing components and the vacuum vessel up to 500 degrees. So that this is because we want to mimic or generate a plasma condition or general condition close to the demo. This is not relevant to ITER, but relevant to demo project demo to come up. The whole scientific program is mostly focused on demo to let's say study the key challenges which are for demo, like plasma exhaust, how to get energy from plasma through the device out, to study the advanced plasma confinement regimes. We can also achieve, for example, negative triangularity, etc. So very large, let's say, scope in the scientific program. The heating, the plasma heating, we will start initially with 3 or 4 megawatts of NBI heating and 1 megawatt of ECRH heating. And later we want to increase up to, let's say, 14 or 15 megawatts in total. So on this picture, you can see how the plasma will look like in this machine. You can see the plasma facing components here. This is the vacuum vessel. And here you can see the toroidal field coils. And outside you can see the toroidal field coils. In this pictures, you can see the different plasma shapes which we will be able to generate using toroidal field coils. So this blue rectangles are PF coils. This black line are plasma facing components, bottom and upper, lower and upper divertors. And this is the red color. The red line is the separatrix. So you can see that we can generate different plasma triangularities, 0.5, 0.6. We can generate double null configuration. We can generate also to some extent the negative triangularity. If we want to study it, let's say with high relevance, if we would have to redo or modify the plasma facing components, which is of course also possible. And we will be also able to generate this snowflake, so-called snowflake geometry. So now, what are the main tokamak systems? So I will try to describe you this generally these systems, and I will also try to explain you which activities have to be done, let's say, to design such quite challenging components. So here you have the list of the main systems. So or parts, the vacuum vessel you can see here on the upper right part. So this is the vacuum vessel with some of the port extensions which go towards the cryostat. On the left you have the picture of the plasma facing components. Then of course you have toroidal field coils and toroidal field coils. So you can see here a system of toroidal field coils and toroidal field coils. Support structure is a big part of the machine, so this is on the bottom left. Cryostat, you can see here. And then we have cryogenic and cooling systems. So this is quite large numbers, large kilometers of pipes and the liquid nitrogen heat exchanger and etc. etc. So the overall dimensions of this machine are, let's say, it's about 6.6 meter high, 5 meters in diameter, and the weight of this machine is about 300 tons. Just for comparison with the previous machine, so the compass tokamak, the weight was 25 tons. So this is more than 10 times heavier machine. Just to explain, this new machine is called compass upgrade, but it's completely new to device. It doesn't have any connection with the original compass tokamak, so it's from the beginning completely new device, fully designed and built and installed in our institute. So now let's go to some individual systems. So I will start with the vacuum vessel. So you can see on the right hand side how the vacuum vessel looks like. So this is the vacuum vessel with some of the port extensions. In fact here you can see the cross section of the vacuum vessel. So you can see this is not a classical D-shaped vacuum vessel, but we wanted to have enough space in the divertor region for example, cryopumping or for diagnostics installation. There are two main, let's say, requirements on this vacuum vessel when we design it. One is that it has to withstand huge ultramagnetic forces, and second is that it has to withstand high temperatures. So because of this, we had to choose. We cannot use standard stainless steel, which is normally used. We had to go for some so-called super alloy called Inconel 625, which includes nickel. And this quite expensive super alloy has to be used because it keeps its properties even at 500 degrees Celsius. Standard stainless steel would not survive such forces at high temperatures. So the temperature and extreme forces, because the forces are a problem because during disruptions, significant part of the plasma current can go via the vacuum vessel. And for example, at the inner part of the vacuum vessel, the total magnetic field can go up to 10 Tesla. So the J cross B force are extreme at some locations. Therefore, the Inconel vacuum vessel has thickness up to 35 millimeters to survive such forces. As I said before, it will be heated up to 500 degrees Celsius using gaseous helium. The pathofacing components will be heated mainly by radiation. And another issue which you have to take into account is that it will be very close to the coils, which will be at the liquid nitrogen temperature. So you have to perfectly isolate this 500 degrees Celsius vacuum vessel from the rest of the world. So this can be done or will be done by 20 millimeters of multilayer, so-called multilayer insulation, which you might know from space, for example, space industry, and also using the cryostat. So this was the only way how to isolate it. You can see on the left-hand side, you can see the system of the tubes and the loops for cooling and heating of the vacuum vessel to 500 degrees. So to design such a vessel is very complex work. A lot of iterations of ANSYS modeling, magnetic modeling, disruption modeling, and all this has to go together. And at the end, after 2 or 3 years of your work, you will finish with the design of the vacuum vessel. So inside the vacuum vessel, you have to have plasma-facing components. This is another quite challenging work, which requires a lot of modeling of plasma, let's say, flows towards these tiles, and also the electromagnetic calculations, because there are forces which act on these tiles. So there are 2 main parts of this plasma-facing components. One is the inner wall emitter, which is used mainly for plasma startup and termination of the plasma discharge. So there are these 8 so-called guard limiters made of tungsten, and the big part is a diverter made of tungsten. So it will call it because it will have up to 100 megawatts per square meter to fluxes, which of course nobody can survive. So we have to dissipate this power to achieve a maximum about 20 megawatts per square meter for a few seconds. So the diverter had to be designed to survive this such power fluxes. In addition, you have to imagine that the whole ring will be heated up to 500 degrees. So it will expand and still have to be perfectly fixed and also still keep centered. So as I said, quite a lot of again challenges from the ANSYS modeling and different kind of modeling which are necessary. This is just the view on how this bottom diverter will look like. So this blue color corresponds to the black tungsten material, and different and there's ways how to fix the whole system inside the vacuum vessel. Then if you go to the PF coils, there's a system of PF of polyfill coils, which has using special material, special kind of copper, which will be cooled down to liquid nitrogen temperature to decrease the temperature, to decrease the resistivity significantly by factor of 10. And special type of isolations have to be used for such applications. The electrical current inside these coils will be up to 50 kiloamps. Again, a lot of ANSYS modeling and electromagnetic modeling. Quite demanding was the design of a bit of Toroidal-filled coils. So this machine will have 16 Toroidal-filled coils. They have 2 parts. One is this lower limb, which is connected then via bolted joint and so-called sliding joint together. Sliding joint is a system of some fingers which in which the coils can move a bit and to let's say tolerate the extreme forces. And so we had to do a lot of modeling how, for example, the current density is in between these fingers. If the contact is good, how is the current density around this corners, let's say, etc., etc. They will again cool down to 80 kelvins, and the maximum current in this coils is 200 kiloamps. Support structure was also quite demanding concerning calculations and modeling, because it has to survive or compensate all the forces acting on the toroidal field coils and on the vacuum vessel. So it will be stainless steel 316 LM, consists of 16 such frames. The total weight will be about 180 tons, and the stainless steel has to be cooled down to 80 kelvins as well. This is because if you cool just the coils, you have to the support structure has to in fact follow these coils, not to create some kind of gap in between. So this has to be cooled down together, and the cool down for the support structure will be about one week. Plasma heating is important system, so we will have two, as I said, two types, ECH and NBI. I will just show NBI now. So it will, because we will start with two 2x2 megawatts beams, like shown in this picture. So it's 2 megawatt units. Each beam is inclined by 7 degrees from the horizontal midplane. The energy will be about 80 kiloelectron volts, and the two big beams will be able to steer, so we can generate counter or so-called co-injection. Diagnostics is a special, big, let's say, part of the work when, let's say, preparing such a device. I will not go into details in this, but there you can see the list of diagnostics and their location to individual ports. Some of them are relatively small, some of them are very quite big. Like, for example, Thomson scattering laser system for measurement of plasma temperature, or diagnostics neutron beam for charge exchange, recombination spectroscopy, etc. Diagnostics have to be allocated in such a way not to be, let's say, not to avoid danger. Let's say, for example, by shine through by NBI systems, etc. So the installation of the location of diagnostics is not so easy, and there is intensive work going on now, let's say, on diagnostic development. Of course, for the first plasma, just a limited set of diagnostics will be used, and the rest will be developed continuously during the operation. Another important system is the Kodak system. So it's a control and the data acquisition system. It has very complex structure shown in this figure. I will not go into details, but the system which serve for slow control and supervision of all the systems based on epics. It controls all the system, the communication nodes, etc. From cooling, cryogenic systems, also connected to protection, personal protection, interlock systems, etc. And then there is real-time fast plasma control system, which will be based on so-called MARTE technology, and this will work with 50 microsecond base cycle. What is the timeline of this project? So you can see indicative timeline. So I will not go into details, but important, I think, message is that the first plasma is expected in 2026. So let's say about 3 years from now. Now, just a few words on the present status of the installation. What you see here is the interconnect complex, how it will look when it will be completely finished. Presently, we have we have available this building, which is the assembly hall. Inside we have the torus hall. In this part we have the control room, laboratories, etc. This is administrative building, which is also ready. And now we are building these two buildings or halls. This is a hall for parts for flywheel generators. This is a hall for diagnostics, power supplies, and gyrotrons. As you can see in this picture or concession, this is how it will look like when it will be finished. So the machine is installed or will be installed in such a torus hall, which is 1.5 meter thick thick walls to shield neutrons and gamma and X-rays. Here we have the control rooms, and on the other right-hand side we have the power supplies, diagnostics, and electron cyclotron heating system, and 2 large flavor generators to provide energy. This is the situation of the construction phases. So this is the phase 1 construction works. So the assembly hall is finished. This is the view of the torus hall. There are heavy doors here, 30-ton doors, for which we can put inside, let's say, bigger parts. This front part of the wall can be dismantled by this big crane, and we can move big components inside. This is view inside the torus hall, so you can see there is a hole prepared for the tokamak. This is the view below the hall, so there are already bolts prepared for mounting of the legs of the machine supporting structure. And I think that's all important. We are starting the installation of the power supply system. The power supply system is completely ready. It has to deliver about 300-400 megawatts for a few seconds. We have installed the thyristor converters for torrido field coils supply. Now we are installing so-called IGBT, 2 rows of large IGBT power supplies for PF coils, and you can see support structure for bus bars, etc. So the installation is ongoing. And this is the part of the second phase of the civil construction works. This is the yesterday status of the construction of these 3-4 hall for power supplies, diagnostics, and ECH. And the hall which you can see behind is a hall for basement for flywheel generators. The flywheel generators are used to accumulate energy and to power, in fact, to provide the energy for the tokamak discharge. We will need a few hundreds of megawatts for a few seconds, which of course cannot take from the grid. So we will have 2 large flywheels. Each of them weighs about 200 tons, and it's sitting on big blocks of concrete, a few meters thick. And these big blocks of concrete will sit on special springs to isolate from vibration the whole system. So this is now again ongoing, and the flywheels has been already manufactured. So this was the status of this project. So I hope I convinced you that Compass Upgrade will offer a wide and in many ways unique parameter range and have very high flexibility of operation to address some of the key issues for in the field of plasma exhaust, but not only in this field, also let's say advanced plasma scenarios, liquid metals, etc. Compass will also significantly contribute to many priorities of European fusion program. I would stress in cost-effective way because it's still a relatively small machine. I didn't mention much, but Compass is supposed to be at let's say European test bed for liquid metal technology in large scale and under let's say the more relevant parameters. The status is that the design has been finished, manufacturing and installation is ongoing now. The first plasma hopefully will be in 2026, and I hope I managed to show you that there is a large range of skills and expertise needed for design, construction, and operation of such a device, and also for exploitation. And you can see that such projects offers you a lot of opportunities in the future. Thank you for attention.
Yes, thank you, Radomir, for your presentation.